Yeah, hello. This is Trey Walters. I am the president and founder of Applied Flow Technology, and I'm going to be presenting today on would Newton approve of how you are using his law? And my co-presenter is Scott Lang. I'm going to present about the first half of the presentation, and then I'll turn it over to Scott, and then he'll finish the last half. So with that, we will go ahead and get started. So, and the subtitle here is how to improve safety and accuracy in pipe force predictions. This is the agenda, what we're going to cover today. Why are transient forces important? How do fluid transients cause transient forces? Some historical context and traditional methods that have been used. How can we calculate forces accurately? Some common pitfalls and mistakes, and demonstration of AFT Impulse and AFT xStream, our transient software products that help engineers get a handle on this important application area. So why are transient forces important? So fluid transients, we're going to discuss in the broad range of fluid behavior as water hammer or surge, which are typically associated with liquid systems, steam hammer, which we're talking about steam hammer in the sense of a superheated steam system with a transient and a large diameter pipe. And this today we're not going to talk about anything related to liquid, vapor, condensation driven steam hammer, but just superheated steam hammer. And these fluid transients, they do cause transient forces. Transient forces can be large, 10,000 pounds, 50 kilonewtons. I've seen them at 5 times that. Depending on the diameter of the pipe, with pressure acting on those larger areas, can be quite large. And so what happens is the resulting stresses on the piping and the pipe structure can cause sudden failure or cyclic fatigue failure over time. So designing a safe system requires accurate transient fluid forces. So let's talk a little bit about the types of forces acting on a pipe. So this one's a relatively simple application where we talk about a point force. And this is simply the gauge pressure times the area. So we have on the right here, we have the internal piping and a pressure coming up, and then an ambient pressure on the outside multiplied by the surface area on that particular face. And so the gauge pressure times the area gives you a point force. That would be the load on a flange, closed valve, etc. If you take something a little more involved and of common interest is a longitudinal reaction on an elbow pair. So here we're not trying to account for all forces. We're trying to account for the reaction. We're going to exclude weight, and we need to look at the difference between elbow pair here, elbows at location 1 and location 2, and what is the fluid force acting on this piping, and then what is the necessary structural reaction to keep that piping in place. AFT, our software, both Impulse and xStream, calls this a difference force set, and what we report is the net force acting on the piping. Okay, so we're going to report the fluid force on the piping that's equal to the reaction needed to be by the structure to support that force and react against it. So the remainder of this webinar, this is what we're going to talk about. Really, is this particular situation here of a difference force across elbow pairs. So let's talk a little bit about the physics of what is happening. And why fluid transients cause transient forces. So let's talk about a case here where we've got piping coming in. We've got a coordinate system here, as you can see, and we're going to consider ourselves really with the x coordinate. So it's going from left to right. There's fluid coming from the left through the piping, and you can see the velocity. It's a constant velocity v. And what we're going to concern ourselves with is what is the force on this leg of piping between location 1 and location 2. Okay, now initially the flow is steady, and right now we're gonna confine ourselves to talking about liquids. The same thing applies to gases, a little more complicated, but the same principles apply. But let's just talk about liquids for the moment, okay? And so we have a steady state velocity, and we're going to say the pressure all the way through the piping has minimal frictional loss, so the pressure is nearly uniform through the piping. And so when you're in a situation like this, the net force, then we have, because of the fact that the velocity is constant, this is constant diameter pipe, the pressure is at steady state with minimal pressure loss, that is constant. There's no net forces. So if you were to plot the force versus time in this particular leg of piping, you're going to see over time the net force is 0. That doesn't mean there are no forces. It just means if you add them all up, they sum to 0, and there's no net transient imbalance that's causing the piping to move or need to be reacted against. It's an equilibrium, okay? At some time later, we're going to talk about somewhere downstream here to the right, a valve is going to be closed. Let's talk about an idealized valve where that valve closes instantly and it sends a surge wave or a water hammer wave moving to the left. So it's moving in the opposite direction of the fluid velocity, and it's moving at the sonic or at the wave speed A, which is close to the speed of sound of the fluid. Okay, now as that wave it's going to start on the right, it's going to make its way through the piping, and at some point in time the wave is going to find itself between point 1 and point 2 at this location right here. At that point in time, what we have is we have the velocity over here on the right is 0, but the pressure has gone up, and you can estimate that with the Joukowsky equation. And we're going to call that P sub J, Joukowsky pressure. Now over here on the left, the wave has not yet reached this point 1 over here. So we have a much higher pressure on the right, and we have a velocity of 0. Over here at point 1, we have a velocity still of steady state velocity and the pressure here, okay? So the net force is going to be pushing the pipe to the right. The fluid is going to be pushing the pipe to the right. And if there's not a structure there, the pipe is going to move. And we'll look at that here in the next slide of what that looks like, okay, from a YouTube video. And you can approximate this force. We're going to drill in on where this approximation has some potential flaws, but on a first order basis, it's frequently not terribly inaccurate to just take the pressure at the location 2, which is the Joukowsky pressure, the pressure at location 1, which is a steady state pressure, subtract them, multiply by the area, and you get a force. The delta P times that gets a force. Now what you're going to see if you plot versus time, what's going to happen is when the wave first passes location 2, traveling to the left, then you're going to see the force go up to some high force up here, and that magnitude of that force is going to equal approximately, it's going to equal this delta P, okay? It's a little more complicated, and Scott's going to talk about this a little bit more later, okay? So that's kind of phase 2. If you wait a little bit longer, the wave is going to progress all the way through these 2 elbows, and it's going to progress all the way go down, okay? When you're at this point right here, what we're going to see is the velocity has stopped everywhere inside the piping because the valve has closed, it's 0. But at this point in time, the pressure is all high. At the Joukowsky pressure, okay? So even though the pressure is high, the flow has stopped, it's a uniform increased pressure, but we're no net force in the x direction. So what you're gonna see is the force is gonna come down and it's gonna go back to an equilibrium force. And now there's no more forces acting, at least on this particular leg 1 to 2. This leg 1 to 2 right here, that comes back to 0. Okay, but during this time that the wave is passing from location 2 to location 1, we're going to see a force profile that looks something like this if the force is instantaneous. Now, if there's a finite duration, the valve isn't closing instantly, it'll have a different shape. But if it closes instantly, it's going to look approximately like this. So what's going on here? So you can go out and find this YouTube video, about 3-4 minute YouTube video. There's a link here at the top. I'm going to pull this up right now and show you a piece of this video at real speed, and then I'm going to show it to you slowed at 25% down, okay? So what's going to happen here, and you can see, is that from the right, and you can't see where the fluid pressure is coming from, but by the motion of the piping, we can determine that there's a valve on the right side that's coming down and then passing from the right to the left and all the way out the other side, and it's going to cause some motion. So let me go ahead and get a I'm going to get our, here we go. So let's go ahead and look at this right here. And so I'm going to play this, and you're going to see this move, and then I'm going to go back and play it at a slower speed. And so the audio, you should be able to hear the audio, and you're going to see what goes on. So first, we'll hear the audio at real speed. Okay, I'm going to try that again because I seem to have lost the video here. I'm going to go back to right before it happens. We'll do it again. Okay, now I'm going to mute this one because when I put it on slower speed, the audio sounds very distorted. I'm going to change the speed so we can see what happens at a little bit of a lower speed. I'm going to take this down to about 25% speed. I'm going to take this back, and we're going to watch the same thing again. And you can, and hopefully, I'm not sure how well this comes across through the webinar, through the feed here, but you can see the motion a little bit. And if you can't, I apologize. You go out to that YouTube link and play it. So I'm going to try it again at 25% speed. And you're going to see the piping move to the right because the wave is coming from the right side. You can see that. And then you're going to see a moment later, it's going to reflect from the left side and come back, and it's going to move the piping again. There you can move to the left that time. Okay. So what we're talking about is in a situation like what we're looking at right now, what is that transient wave doing between these two elbows? What force is it exerting on the piping, and what strength of support is needed to keep the piping from moving or just having to react to handle that? So you don't have damage to the supports or to these, like for example, there's flanges in here as well. So let's carry on, and we're going to go back to our PowerPoints, and we'll go on for one more page here. Okay. Let's talk about some of the historical context. So there's a method which doesn't really have a name that we have given a name called the endpoint pressure method. And what it essentially does is it just takes the pressure at location 1 and from location 2, and it subtracts those, similar to what I showed a couple slides ago. Okay, and so the reality is this is quite a bit more complex than that, and that what we'll call the endpoint pressure method has some significant flaws, and we want to alert you to those here today. So because of the fact that this is such a complex phenomenon, and if you go back 50 years, 60 years, 70 years, and we have some of our predecessor engineers working with slide rules before they even had calculators. They didn't have access to a computer. They're trying to do their best to determine how to keep the piping supports safe and be able to design those. And so with a slide rule, there's no way you're going to be able to do the types of things that you can do today with software such as like Impulse and xStream. Okay, so simplified methods were used, and they were really appropriate. They were not perfect, but for the day, we're talking 50, 60, 70 years ago or before, they were as good as you could do. Our point today is you can do much better, and we shouldn't be using these simplified methods anymore because they can be quite misleading. Okay. So this is the endpoint pressure method. It estimates the force between location 1 and 2 by just taking the pressure times area loads at the end of the system. And again, only feasible if you're doing force calculations by hand with a slide rule, or let's say a calculator back 50 or 60 years ago. Okay. It neglects some things. There's more things in Newton's equation than just P times A. Okay. And that's where we talk about would Newton approve of what the methods that we use. And Newton would say no. And if we could bring him back today, he would say no, you have to account for everything in essentially the F equals ma equation. And if you're only doing pressure times area, you're neglecting some things, okay? That's what we want to highlight today. If you want to account for everything, it is important, and often dominant is the P times A, but there's also forces due to friction, there's forces due to internal pressures, and especially if there's diameter changes or valves or something, a high loss valve inside or an orifice, and there's also forces that result from momentum change, okay? So using the endpoint pressure method, this traditional simplified method, is not a complete application of Newton's laws, and Newton would not approve of that. And so we're going to talk about what would Newton approve of. So here is a method that Newton would approve of. It accounts for everything in his second law. Okay, this goes back really to 15 years ago, and I actually worked on this personally in AFT Impulse version 4. And back in 2006 timeframe, in 2007, we started to implement for the first time the ability. I mean, our Impulse software goes all the way back to 1996. Had always had the ability to calculate all the fundamental things you need to do Newton's calculations here. All the pressures and velocity and momentums, you could in principle do it, but we didn't have the feature where you could just tick a box in the software and say, show me the forces and graph them for me, and show me the maximum magnitudes and positive and negative. And so we started working on this in Impulse 4 in the 2006-2007 timeframe. I actually made a trip down to Houston and talked to one of the leading software suppliers at the time, which was the people who developed Caesar 2 software, and asked them, how do people do this? And they said, essentially, that they just use this method right here, P times A, endpoint pressure method. So we went and faithfully started using that method in Impulse 4 before it was released. This is during the development of Impulse 4, and we found out pretty quickly it has some flaws. It doesn't include everything. And so we sat down and we called them back, the people, the Caesar 2 developers, some really smart people, and asked them, said, you guys aren't accounting for everything. And they kind of shrugged their shoulders and says, well, we're pipe stress guys. We're not hydraulic guys or water hammer guys. And we said, okay. So we sat down and with Newton's method and came up with all all of the parameters that need to be included. And we put that into Impulse 4. And so since Impulse 4, and that was released in 2007, you've been able to do a complete calculation of all of the forces and get a complete force balance, which is accurate in both magnitude and direction since Impulse 4 for the last 15 years, okay? At that time, we didn't give a name to it. We just called it the forces in AFT Impulse. Now we've come up with an alternate method I'll talk about in the next slide, but so we have, now that we have two methods that we can use that faithfully represent Newton, we give them two different names. So we are now calling this method that we've essentially had since 2007 called the component reaction method. It does not ignore any force terms. It includes everything from a transient water hammer surge fluid transient point of view. And it works by summing up every component force between the elbows, okay? Now, the endpoint method is going to only focus on this pressure acting on this area, this pressure acting on this area. There's other things involved here that we have to account for. So one of the important ones is what's the friction in this line. It depends on how long the line is and what the viscosity is of the fluid, how viscous it is. There's also got friction in this line. You also can have pressure forces acting on, let's say, a valve. And there's also momentum changes that happen across a valve or an orifice or some sort of a fitting or component that is in between the two elbows to the left and right. There's momentum changes because in steady flow, there's no momentum change if it's constant diameter pipe. But in our case, we can have momentum changes because when there's a water hammer wave, there's a different velocity on the left than there is on the right, even for a constant diameter pipe. You have to account for that. And so if you take all of the pieces that we show right here and you get and you take something that comes from if you're good enough to do it with a hand calculation, you can do that, pretty complicated, but software like our Impulse software and our xStream software, it has all of this information, it has it. So the question is, how do we pull all of that out and then actually show what the unbalanced force is and then tell the users, okay? So that is what we do in Impulse. And Impulse really still uses today, it uses the component reaction method. Let's come a little bit closer in time here on in 2020. So the last couple of years, we're working on a new transient software, some of you hopefully have heard of, called AFT XStream. XStream works by on doing something a lot more complicated than what Impulse does. Is it attempts to simulate what's going on the fluid transients in gas and steam systems. And I can tell you from experience, and so can Scott, as Scott ended up working heavily on the development of that particular product. As I was the original developer of Impulse back in 1996, and I worked on it very heavily all the way up through version 5, a little bit version 4 and into version 5 about 10 years ago. But Scott was working real heavily on this. And so we sat down and we said, okay, well, forces can be important in gas and steam systems. How do you calculate them? Okay, so we're working on this. And we realized, and we expected this was the case, and it was, is calculating forces under compressible flow. It proved much more difficult than it did for, well, Impulse is not incompressible. It's liquid flow is what I'd say, liquid flow, where there's compressibility, which causes the water hammer wave, but you can treat the density as roughly constant, is probably the way to put it. So, so trying to do this for truly compressible transient flow was a lot more difficult. And so we needed a different method, which was also complete, would be nice. Otherwise, I mean, we could have done it, and we still could today, but that was just going to be tough. So we started digging around, and Scott actually dug into this. We talked about it back in 2019, 2020, and he came in with a whole new method, which really is, it's still new to him, but it all revolves around how do you draw your control volume, okay? What's the control volume? And so the component reaction method essentially did not draw the control volume outside around the pipes. It drew it essentially on the inside of the pipe, around the fluid, okay? And that becomes the previous method that we use in Impulse called the component reaction method. But Scott realized that if we drew a different control volume, we could actually estimate the forces that are imbalanced to the fluid transient differently. Now this method, now that we have two methods, we want to give it a name, and we have named this the acceleration reaction method. And what it does is that because of the way that you draw the control volume, all you need to account for, you can actually ignore all the pressures. It's kind of nice because they exist, but they all cancel out. And the only thing that doesn't cancel out are these acceleration terms. And I'm gonna let Scott dive into this here. But essentially, what we're going to do is we're going to look at the fluid acceleration within the control volume, and that imparts a force. Now, we have these programmed like in our Impulse software, even though users don't have the option to choose it, but we can do both methods in Impulse, both the component reaction method and the acceleration reaction method. They give the same results because they're both basically just two different ways of doing two different control volumes. So we've tested this real heavily in our software and in Excel, and they give the same results. So there's one is, I would say, is more suitable for liquids, and then which is the component reaction method is suitable for that. It's not as suitable for gases. And the acceleration reaction method works both liquids and gases quite well. It works, it always is going to work. It's just easier. It's easier to determine this. So I'm going to let Scott dive into the details on this. And so the acceleration reaction method was first released to the marketplace in our AFT XStream version 1. It was in first quarter of 2021, so it's been out in the marketplace a year and a half, and it utilizes this acceleration reaction method. So there's some accompanying information attachments to this webinar, and part of the genesis for this, if you haven't been reading all the nitty-gritty details, is Scott and I wrote 2 papers for the ASME Pressure Vessel and Piping Conference in July of this year. It was in Las Vegas, and we presented both of these methods there. So they're now out into the literature. You can find them on our website. And that is where you want to go. If you want to read all the nitty-gritty details, is go read those papers. Today, we're kind of summarizing some of those key points. And with that, I'm going to turn over the presentation to Scott, and I'll hang around for any questions that you guys might have. And so what I need to do now is I need to change the presenter to Scott. I'm going to do that. Scott's going to pick this up and take this to conclusion. And I might jump back in. I'm going to mute myself, but I might jump back in at the end for questions. So thanks for your attention, and we're going to go over to Scott now.
All right, thank you, Trey. As Trey's mentioned, what we do not want to do here is making sure I'm sharing the right screen here. Okay. is make this sound like something that is very complicated, that if you want to go do forces correctly, you are going to have to go through a lot of effort to try to figure out what exactly terms you need or anything. Really, this is all just a explanation of the background. We really want to encourage you and say, this is very easy with the right kind of software like Impulse and xStream. So I'm going to jump into some background stuff, but keep in mind that practically it's not this complicated for an end user. So how do Newton's laws apply to force calculation? Newton's first law states that a body remains at rest unless there's a net force, so everyone should know that. And what this really means in our context is that the pipe does not move, or at least we're hoping it doesn't move. We want to figure out what kind of supports to design to make a reaction large enough that it won't move during some fluid transient event. So the net force on the pipe must be zero. Newton's second law states that changes in momentum are coupled to net forces. And we can get these changes in momentum a few different ways. So we can get them in flow around bends, through area changes, across transient waves, and in accelerating compressible flow, even in steady state. So in any reasonable situation, you're going to have momentum terms. In some cases, they might be small enough that you could ignore them without huge impact, but in some cases, they are very significant, and knowing whether or not you can ignore them is a tricky thing. Newton's third law states that every action has an equal and opposite reaction. So this elbow pair reaction must oppose the net load in the pipe, and internal forces like those due to flow around bends must also be opposed, and we'll use that kind of internally to this method shortly. Okay, so the component reaction method. As we've seen, it's talking about all of these individual forces in a elbow pair here. And the key thing here is that this analyzes the pipe directly. What we're looking for here is what is the effect of the fluid on the pipe and what reaction on the pipe is needed to oppose that net effect. So again, the pipe does not move, or at least we hope it does not move. So Newton's first law tells us that the net force on the pipe has to be zero. And that net force includes both this reaction, external reactions provided by either fluid supports or the piping itself, and the fluid forces acting on the pipe. So the friction, momentum, pressure, everything like that. So we have a simple equation here. Fluid forces plus some reaction force has to add up to zero. And because that net force is zero, we can conclude that the reaction forces exactly oppose one another. So again, AFT software is going to report this net force acting on the pipe. So the reaction would be the negative of that value. All right. So these component forces, there's various different kinds. As we've mentioned, pressure forces, which are just pressure times area. Friction forces, which we can calculate with friction factor, flow, viscosity, interior wall area, everything like that. Very simple things. And there's forces due to momentum changes, which are a little bit more complicated. I'll talk about just one of these cases here, flow around the bend. So we have down here flow coming in from the left around this bend and being redirected up towards the top of the page. And this has a momentum change even in steady state. So something has to be redirecting this fluid from left to right to vertical. And that is a force acting up and to the left here, this blue line here acting on the fluid. And we can calculate that force with Newton's second law. So that's relating this change in momentum to the force. And Newton's third law is applied to reflect this local force onto the pipe. So the fluid requires this force to the upper left. That means that there must be a force acting to the lower right on the pipe. And this is a kind of multi-dimensional case here. The forces that we are talking about, these elbow pair or longitudinal forces, they might be acting only in the x direction here. So we really are only concerned with maybe this x component, which there would be a similar x component acting to the right on the pipe in red. Okay, so the acceleration reaction method, as Trey has mentioned, this is a very different approach, but we're trying to capture the exact same effects. The terms that you would see in here are different, but the application or the approach is the same at the highest level. We're still just applying Newton's laws. Really, the difference is how we draw that control volume. So instead of just looking at the pipe itself, we're going to look at the pipe and fluid together. And because we've drawn this control volume outside of the elbows here, for example, there's no pressure acting on this control volume itself. So the pressure in the pipe is acting on this elbow, trying to force it to the right, but that's all internal to this control volume. So the only forces acting here really would be maybe on this bottom surface, but they would be vertical, and those aren't going to affect this horizontal reaction. So what does affect this horizontal reaction if there's no forces acting from the outside here? Well, really it's just fluid acceleration within the volume. So, and this is really saying we're going just to apply F equals ma to this entire system. And that's just saying that the reaction is going to be equal to the fluid acceleration within that volume. So how do you get acceleration? Well, that's due to these fluid transients. So as Trey had demonstrated, especially with the video, you get some pressure wave coming in here, perhaps from the right, up through the system. And as that pressure wave is traveling, it's very rapidly halting the fluid. If this was a downstream valve closure, for example. And that very rapid halt in fluid velocity is an acceleration. So really all we have to do is calculate that acceleration, and really the sum of all of the accelerations in this control volume. And with that, we can directly calculate this force. All right, so some common pitfalls and mistakes. And this slide is in here really just to say, if someone is looking at all this math and they say this is too complicated, I want to do it the easy way. This is really to encourage and say, why is that potentially a problem? Why can't I just do it the easy way? One reason is that you might not be appropriately accounting for the sign of forces. So some forces, like pressure forces, are relatively clear in their direction, but others, like momentum forces on the nozzle, are less clear. So it's very easy to get tripped up with looking at things. You might think of the example like a fireman holding a fire nozzle and say, well, clearly that fireman has to hold the nozzle forward, otherwise it's going to go backwards. So the force on the nozzle must be towards the fireman. But that's really not the case. If you cut the nozzle off of the pipe, it's going to go forward, not backwards. So if you don't add up all of those signs correctly, you're going to get some kind of incorrect result, depending on which signs you got wrong. So you have to be very careful about that. The common thing, neglecting terms as always small. This is really perhaps the main way people would end up with the endpoint pressure method and say that that is totally fine, is that the pressure forces are often extremely dominant, and sometimes these other terms are very small, and that's not a big problem to ignore them. But other times they are very substantial, which we'll see in an example here shortly. And there's really no way to know ahead of time if these forces are going to be substantial enough, friction or momentum, that they're going to impact your reactions substantially, and maybe change the conclusions you make about what kind of support you need. So our argument would be, yes, sometimes pressure times area is fine, but you really don't know until you actually do it the right way, if that's okay. So don't guess, just do it the right way the first time. Another potential problem is neglecting a rigorous transient flow solution. So the accuracy of these forces depend directly on the accuracy of the underlying transient flow solution. So you could use shortcuts like the Joukowsky equation and say, well, if I instantly close some valve somewhere in the system, I'm going to get a pressure rise of 100 psi, for example, and I can just multiply that 100 psi times my pipe area of some 4-inch diameter pipe area and get some force. That can dramatically misestimate the true force. And I say misestimate here on purpose because you could get a force that is lower than the actual force here. You could also get an estimated force that's much, much higher than what you would really see causing you to spend way too much money on your support system. So you don't really know, again, until you actually do a true transient solution, what those true forces would be. And another thing that we've seen is people may be cognizant of all of these things and they say, yes, I know there's a huge force, 10,000 pound force, but these transient forces are fast. Those waves are moving near the liquid speed of sound, so that elbow pair might only be loaded for a few milliseconds. And we have seen people say that we can ignore that because it's not a static load. But while that is true that there is generally some kind of mechanical tolerance for short duration loads, and you have different allowances and codes for those types of loads, but even so, that dynamic load can still far exceed any limits that we've seen specified, in code. So it'd be very dangerous to just say, this is a fast event, so we're going to ignore this. Even if it doesn't destroy the system immediately, you're going to be putting a huge amount of stress on your joints, and you may very well see a failure later on down the line. All right, so an example here, this is going to be a crude oil piping rack. And this example is built off of similar types of systems that we've seen. So this isn't just an example constructed to show cases where these terms are big. This is a system that we believe is reasonable. So it's going to be modeling a crude oil pipe rack within a tank farm. So we have a relatively long straight length of pipe bounded by two right angle bends. So this elbow pair that we've been talking about. But we're going to make it a little bit more complicated than just two elbows. It also contains a valve that changes in position from 100% open to 10% open over 3 seconds. And this is going to be using a realistic valve profile. So I believe this was a ball valve. And we're going to see a reduction in flow area from 8 inches to 6 inches inside of this straight length of piping bounded by the bends. And we have an initially high velocity, 11.5 feet per second in the 8-inch pipe, and of course higher in the 6-inch pipe. Again, that's higher than maybe most people would recommend, but it's not unreasonable. It's definitely within the realm of values that we have seen. And here's just a simple diagram of the system. So we have some pretty long piping upstream and downstream, this pipe 1 and pipe 7. And we have these two elbows here. And pipe 3 is this 8-inch pipe. It reduces in size to this pipe 4, 6-inch pipe. And we have this valve that's going to make a partial movement and propagate some waves upstream and downstream. So I'm going to load this up, or I have it loaded up. I'm going to switch to this in Impulse. And that's exactly what this model is. So I just have an area change here in a valve. And this model can run as it is. I'm not going to go into the details of how to define anything with Impulse. We've got plenty of resources on that if you're curious. I'm just going to demonstrate very quickly how easy it is to create this force set, as we refer to it in our interface, to be analyzed. So I have my system entirely defined, and I want to know what the force is between this elbow at J3 and this elbow at J6. So I will come into my analysis setup here and come into my force definitions, and I want to make a new force. So by default, this is going to be a difference force. And for the most part, that usually works fine if I wanted a force across one pipe. Here I have 3 pipes, so I have to somehow indicate to the software what pipes are in the set that I want to analyze. So I'm going to drop down my force type here to difference with 3+ pipes. And I want it to start at the beginning of pipe 3. So I just choose pipe 3 and I see it says length to start node and feet is 0, so that's the beginning of pipe 3. And I want it to end at the end of pipe 5 here. So I can choose pipe 5 and automatically it assumes that that's what I want. It says length to end node, and I know that that is actually the end of the pipe. And because this is 3+ pipes, I have to convey somehow to Impulse what pipes are in this. So I've created a pipe group beforehand, and I have to choose that here. And this is just really just a group in another part of the interface saying this has pipes 3, 4, and 5 in. It's that simple. I can say okay, and that I'm actually done. I can just run the model now. It might take a moment depending on how big it is. And it's cranking away on these numbers. As Trey mentioned, the default here is it's going to be calculating with that component reaction method. There are some advanced ways that you can switch it to the acceleration reaction method, but they both give you the same result, so there's really no reason to worry about that. And when it is done, I can come to graph results, and I have a forces tab in here in my quick access panel. I can just click on that and check the force to be graphed and say generate, and that is it. So this has done all this complicated work for you. This would be very difficult by hand, and we know that because when we verify this ourselves, we've done it by hand, in an Excel spreadsheet with a simpler system than this, and it is not easy. But for you, it is. You can very quickly see how the force is behaving here. It rapidly comes up to a value around 3,000 pounds force positive, drops, and has a few more peaks as that wave is reflecting back and forth through the system. So this is obviously a significant force you want to be aware of. You want to design this correctly. So I also have open here another example. This is the same system. And this graph at the top is the same graph that we just saw, that I just generated. But at the bottom, I have a different graph. And this different graph has been generated by ignoring momentum and friction effects. And as you can see, there's a dramatically different behavior here. This is predicting a much larger force in the wrong direction. So you could completely either over-design your supports or just design them in the wrong primary direction, I guess I would say, if you use this more simplified method. And I would say further that this more simplified method presented at the bottom here actually includes more pressure forces than just the endpoint pressure forces. So if you resort to the endpoint pressure method, your results will be even worse than this. So don't rely on this. It can very easily be dramatically different than the true values. So that is the beauty of computer simulation, is we can get that very easily. And just a final point on this example, this does come from, and the next example I'm just going to talk about also comes from our papers. So if you want to see some more results about these and some other cases that have other terms more important or less important, that is where you can see all of these examples. They were all built in our software. So you can see kind of how that works. Okay, so an AFT XStream example, I'm going to talk about now this turbine supply line. So the turbine supply line is, you have some steam power plant, steam turbine, something really, it doesn't matter if it's a turbine or not. What we're saying is you have a large diameter pipe with steam, and it doesn't have to be traveling that fast, but you have a lot of flow and just a lot of mass due to the diameter. And if you halt that steam turbine or whatever that end device is, perhaps by closing off the flow with the valve, just like with liquid flow, you're going to generate a wave that travels upstream. And one of the key things here about this particular example is that in the last example, this endpoint pressure method dramatically over-predicted the magnitude of that maximum transient force. And this is not always the case. So in some cases, these simplified methods underpredict the force. And in this extreme steam turbine example, turbine supply line example, we see that. So I'm going to show some results from an AFT XStream model. As you can imagine, running a transient analysis on compressible flow takes a little longer, and you guys don't want to wait while I do that. So I'm just going to show a couple graphs on the next page. But the idea is that this is analyzing the closure of a valve over 100 milliseconds, so very fast emergency closure, in about a 30-inch steam supply line. And the elbow pair of interest is about 1,200 feet from the valve. So here's the simple diagram of the system. There's a lot of elbow pairs in the system, and our flow is initially from right to left. And this assigned flow junction here is representing a stopped valve, so it closes the flow off very quickly, and that's going to propagate a wave to the right. At some point, it's going to enter this pipe 13, and that is going to cause a reaction on that leg. So even with accurate flow results, that endpoint pressure method would underpredict the maximum forces by, in this case, several thousand pounds, if not more. So here is an example graph for that pipe 13. The acceleration reaction method is this black line, predicting a force around 21,000 pounds. And the endpoint pressure method is predicting a force a little bit higher than that, maybe around 24,000 pounds. So not a huge difference, but it's certainly enough that maybe it might impact, the conclusions that you draw about what kind of supports you need. And I'm not going to go in great detail about this, but that's not the whole story with the compressible flow. With compressible flow, you can get effects like wave steepening. So these are all these different legs in the same system. From left to right, they're farther away from that turbine stop valve. And if you do the endpoint pressure method, and especially if you do that without a transient analysis and some typical estimations that we've seen used in industry, you might come to the conclusion that the forces are around 15 to 20,000 pounds throughout the system. But if you actually do this analysis with an accurate transient flow solver and an accurate transient force methodology, you can see that as that wave travels down the system, it steepens and causes this force to increase all the way up to around 45 to 50,000 pounds. So that would be a serious problem if you had designed the system to support only 20,000 pounds. Even if you had added a safety factor of 2 on this 15,000 pounds, you would still be up here at 30 to 35,000 and far under the maximum possible load. So this is our very strong encouragement to say, don't estimate these things. If you use these rule of thumb approaches, you can get values that are less than half of the true value. So you can't even necessarily rely on safety factors. And because it's so easy with the tools that we're presenting you, again, we're just really trying to say, use the simulation, get the right forces, and don't guess. And with that, I think that is all I have. So thank you for joining us. And if you have any questions that you haven't sent our way already, I'm not sure if anyone has done so, please feel free to send them our way after the webinar, and we will certainly answer those for you.
Yeah, this is Trey, and I'm jumping back in with Scott now. And so Scott, I've been monitoring the chat and the questions, and nobody has asked any yet. So Scott and I can hang out here for a few minutes, and if you guys want to type those in, we'll do our best to answer them. And if we can't do that timely, we'll collect them and get back to you after the webinar is completed. But looks like there are no questions. We had a perfectly clear presentation on a perfectly easy topic, so no questions. So I would encourage all of you. Is there people here they're raising a hand? I'm not sure, Walt. We have another person on here. If somebody's doing raising a hand. Cannot tell.
I do see a question here about collaboration with Caesar and AutoPipe. And I would say, I guess you saw this answered maybe by Walt, but that is another piece that I didn't demonstrate here that's very simple. We do have a way to export these forces directly into those programs. So if anyone has themselves expertise in Caesar 2 or similar program or another department that does that, it's very easy to take that extra step.
I'm seeing a question here about reciprocating compressors. So I don't know, Scott, you want to take that? And I think it must be about like what the forces are. So.
Right. So what about momentum effects on forces in a steady state dynamic system like a reciprocating pump? I would say in that case, you certainly will have forces. And we do have a couple ways that you can try to model, pulsating device. You can have PD pumps defined in certain ways in impulse. And you could do that with an assigned flow junction stream. If you know exactly, what this flow pulsation is, then you could use our normal force tools. And on top of that, we also have these pulsation modules. So you could figure out, what is worst case pulsation levels and pressure, and then again, you can, on top of that, look at the forces. So you can figure out the worst case forces for the pulsating loads. So hopefully that addresses your question, Kelly.
Yeah. So yeah, if you're trying to get forces, you're going to need to look at that in the time domain. And so basically, it's representing your recip compressor boundary conditions, which we have some guidance on how that you can do that. And so yeah, it is possible to do that and be able to get forces from reciprocating compressor. So, and then a bunch more questions are coming in here. So I don't know if you can see them all, Scott. So.
I can. I do see a question about two-phase flow, and that is a great question. We don't at AFT currently have a product that does two-phase transient flow, but certainly, that is a concern for forces. If you have slug flow or things like that, that is going to be a serious concern. I would say, this methodology that we presented should handle that kind of situation, but again, you need that underlying transient solution, and AFT does not currently have that.
Yes, and to add on to what Scott is saying is that especially the acceleration reaction method, the second of the methods, we don't have the ability to simulate that as a commercial tool, the two-phase. But if you can come up with that two-phase transient, then the acceleration reaction method that's presented in the papers should be able to help you determine what those forces are. There's also another question on where the publications are. If you look, there should be some attachments or handouts. There's handouts with this presentation, and you can go, and there's something called ASME Accurate Forces, Part 1 and Part 2. You can get them from the handouts from this presentation, or you can actually go to the AFT website and go into the area where we talk about the Learning Center, and you look for technical papers, and you can download those from our website. There's another question, Scott, here I'm seeing about the what version of Impulse is shown here. And the version that we're talking about today is Impulse 9. I think the features are relatively the same between version 8 and 9. That would, but I don't know, maybe the ability to do 3+ pipes maybe was something we enhanced in version 9. I can't recall if that was version 8 or 9.
We may have made it a little bit easier. I'm not sure, but everything that I showed you can do in Impulse 8.
Yeah.
I see another question here of, can the software predict the force flows on a horizontal split case pump in which the suction inlet comes in from vertical and exits horizontal? I would say more complicated arrangements like that, we can't just directly say, this is the force. But with that point force that Trey had mentioned, we can tell you the force is acting, at different locations in the system. And you would have to take those and make some conclusions off of them. So we can give you good information about the hydraulic loading that pump might be seeing, but there is some work on your end that you'd have to put in to interpret those.
Yeah. There was a question about somebody having version 8 and getting to version 9 of Impulse. And so the answer to that is if your company has an annual agreement to get those version upgrades and they exist and you can get those, you can just contact our support at aft.com department and we'll get that to you. And if not, then you can contact our sales at aft.com department and they can tell you what it takes to order for you to get upgraded to the version 9. There's a question here about screening method criteria. Scott, you want to take that one from Natalie?
Sure, that is a fantastic question. If we have any screening criteria to recommend cases that require analysis. And actually, Trey had authored a couple papers about this at the same pressure vessels and piping conference that these force papers were presented at. And there are methods out there that you could do, to estimate, how important force analysis is for a particular system, or roughly, what kind of loads you would see. And for impulse, that might be something like using the Joukowsky equation with the pipe area. But from my knowledge, those methods are very coarse. And honestly, I'm very hesitant to say, go ahead and go do that. There's ways that you can improve those methods, but by the time, in my personal opinion, you get to some screening method that is sophisticated enough to make sure you're making the right decision, you will have put in just about as much work as it would have taken just to analyze the forces with the simulation like we've shown. So there are some things that you can do to estimate what the loads would be, but you have to be very careful with those. I'm not sure.
I'll add on. I'm sorry, Scott, go ahead and finish.
Go ahead. I was going to ask if you wanted to add anything.
Yeah, I'll add on to Natalie's question is that especially for extreme and the forces, there's a traditional method called the Goodling method that's been used for the last 40 years. And at the same conference where Scott and I presented these two papers on the forces, I presented two papers on doing loads and steam systems. And I showed why the traditional method for the last 40 years, how it's extremely flawed. With modern insight from 40 years ago, I think it was very good, but based on today's criteria, it is flawed. And I came up with a new method for screening. It's an improved method of screening for steam hammer loads. It's a little easier to do that in steam hammer when you kind of know what the application is with the turbine supply pipe. A general screening method I don't think exists. I would agree with Scott. It's going to be even harder to do that with impulse because as it's going to be really hard because those other terms like the friction and the momentum can be even more dominant. So I would be very careful with that. I think, Scott, we're down to the final 2 minutes, and there's another question in here about column separation. So
yes,
go for it. I'll jump in when you invite me.
Right, and that is another great question. So the question essentially is, paraphrasing, I have cavitation in my system, and that is causing some extremely high forces. What do I do? And that is a very challenging question, and unfortunately, my answer is not going to be super great. It's going to be a little vague. The best thing you can do is prevent cavitation. That phenomenon is obviously going to cause these huge forces, and anything you can do to avoid that, that is really what your primary focus should be. And if you can't prevent it, I see that the next question, what if we are unable to prevent? Then unfortunately, I would say the force method that we presented, it is generated assuming that the fluid is single phase. So it doesn't necessarily directly account for cavitation. And again, at a basic level, a mathematical level, it should be able to account for that. But the cavitation modeling itself is uncertain. So Impulse, will do what it can to model that and give you some kind of estimate of what the pressures are. But those are definitely estimations. We've seen tons of literature here at AFT about cavitation modeling, and the unfortunate truth is that it's a very uncertain science. And if that's uncertain, you're going to get uncertain pressures, which means your forces are going to be uncertain. So you could potentially take, force results out of Impulse and add safety factors to them or something, but we really would caution you against that. And in fact, and I'll let Trey, you jump in and explain a little more about this, but there's a couple papers you authored on that.
Yeah, we're in the final minute here, so I'll just conclude, and then we'll conclude at the top of the hour. But if you go to our website, this is asked by Rahul Kumar, and I actually worked with a client at AECOM to develop some criteria for doing forces under cavitation. It's not great, but it's the only thing that exists out there. There's 2 ASME papers, one on pressures under cavitation and one on forces. I just encourage you to go to our website, aft.com, go to the paper where there's the Learning Center, and go to our technical papers, and they're from 2018, ASME PVP conference. So, and with that, I think that the presentation is going to be, there's a final question from Oscar, is going to be available as a recording, and you'll be emailed that when we conclude here. You'll get a follow-up, and then it'll be available on our website as a recorded one. So, and Rahul Kumar, you feel free to contact us directly. We'll answer your questions a little bit further if you'd like to. So I think we're going to conclude with that. We're at the top of the hour. Thanks for all of your great questions and your attendance, and I wish all of you a good day.
Yes, thank you all. Have a great day. Bye.